Everything started at the moment of the Big Bang, 13.8 billion years ago. Time and space begin when a tiny point full of energy starts expanding at an incredible rate. An unimaginable amount of energy transforms into matter and antimatter. But shortly after, all antimatter has disappeared and only a tiny fraction of matter is left, still enough for all stars and planets in our universe. In the first 3 minutes, protons and neutrons form the lightest nuclei, while the universe continues to expand and to cool down. But it takes almost 400,000 years until hydrogen and helium atoms can form. Now the universe has become transparent. Light from this era can still be seen today as the cosmic background radiation. Gravity begins to pull the hydrogen and helium together. Stars are born. Fusion inside the stars forms heavy nuclei, the base of life. And these building blocks are thrown into space when stars die in giant explosions. After 9 billion years, gravity pulls some of these remnants together to form our solar system with our planet Earth, where evolution gives rise to life, intelligence, and consciousness. We understand the primordial state of matter before protons and neutrons formed. Will we find the reason why antimatter and matter did not destroy each other completely? Will we find the particles that make up the mysterious dark matter? The discovery of the Higgs boson has proven the existence of the bright angular Higgs field that gives mass to all particles. Will its study reveal any new phenomena? And will it tell us more about dark energy? The LHC will bring us closer to an understanding of our universe.
On a site in Meyrin, a small village near Geneva, work for the new laboratory begins. Within a year, the farmland is transformed into a large complex of workshops, offices and buildings to house the new accelerators. The 5-meter thick walls of the synchrocyclotron building soon emerge. While the different parts of the new accelerators are manufactured in several European countries. The synchrocyclotron's magnet coils require particular care to pass through some of the Swiss villages on their way to Meyrin. As components arrive, they are assembled with great precision. Everything starts to take shape.
The synchrocyclotron emerges, piece by piece. Some 54 4 elements are put together for the magnet frame. A total of 2,500 tons of steel. Next, the two 7.2 meter diameter magnet coils are installed. With a current of 1,800 amps, they generate a magnetic field of 2 Tesla. The rectangular vacuum chamber is fixed inside the magnet. A system of large vacuum pumps is installed to evacuate the 25 cubic meter chamber so that protons can circulate unimpeded. This is followed by the installation of 2 D-shaped electrodes inside the vacuum chamber. Together with these electrodes, a radio frequency generator creates the electric fields. That accelerate protons from a source inserted in the center of the vacuum chamber. In summer 1957, the synchrocyclotron is ready. And CERN's first accelerator comes to life. The purpose of the synchrocyclotron is to produce and study new particles. Before accelerators were available, such particles could only be observed in cosmic ray experiments. The new machine accelerates protons to 80% the speed of light, producing millions of new particles when those protons collide with the target, giving scientists the opportunity to make systematic measurements. Operation of the SC requires a sequence of actions. Massive pumps extract the air from the vacuum chamber so that protons do not collide with gas molecules during their acceleration. In the proton source, hydrogen gas is ionized and a cloud of protons is injected into the middle of the synchrocyclotron. The accelerator makes use of magnetic and electric fields. The magnetic field is produced by a current of 1,800 amps flowing through the coils of the huge magnet. 2 D-shaped electrodes with opposite polarity are fixed inside the vacuum chamber in the middle of the magnet. Protons have a positive charge and are drawn towards the negative electrode as they traverse the gap between the electrodes. The magnetic field forces them to follow a circular trajectory, and they return to the gap after 1/2 turn. Meanwhile, the radio frequency generator reverses the polarity between the 2 electrodes. The protons are now attracted to the opposite electrode and gain more energy. This process is repeated over and over again. Every time the protons make a 1/2 turn, they are whipped around faster and the radius of their path increases. After more than 100,000 turns, they have reached an energy of 600 million electron volts and move at 80% of the speed of light. They are now close to hitting the target, and the first experiment can begin. 1967, a new idea takes shape called ISOLE, an isotope separation device. Protons from the synchrocyclotron collide with target nuclei that are split into short-lived fragments, which are then rapidly scrutinized in experiments. The study of such short-lived nuclei with too many or too few neutrons helps to understand how heavy elements are produced in exploding stars. The synchrocyclotron accelerates its last beams in December 1990. After 33 years of an exceptionally long and successful career, the SC is retired. Following the synchrocyclotron's construction, CERN built bigger and bigger accelerators. The proton synchrotron, the intersecting storage rings, the superproton synchrotron, the large electron-positron collider, and the Large Hadron Collider. Many important achievements were made, some of them being rewarded with the Nobel Prize.
the drift chamber, which revolutionized particle detection, the cooling of particle beams, the discovery of the carriers of the weak interaction, and the Higgs boson, which proves the existence of the Brout-Englert Higgs field. In 1989, Tim Berners-Lee, while working at CERN, created the World Wide Web, which has since changed our world forever. The Large Hadron Collider will continue to run at higher energy and higher intensity, with more than 11,000 scientists from over 100 nationalities, hoping for new insights into the secrets of the universe.
I think that the curiosity and the need to do research is inside is a part of our humanity, so there will be always a CERN. So there will be CERN in the future.
What started once as a vision for European science has grown into a unique model for global scientific and technological collaboration. CERN demonstrates how science can unite nations and contribute to a better world.
The elementary particles are the smallest object that we know. Their dimension is smaller than 10 to the minus 16 centimeters. Are you familiar with what I'm saying? 0,15 zeros to 1. The elementary particles are smaller. Where these elementary particles have been found, three of them are the constituent of everything that is around us. You know that we are made by atoms. The atom is made by electrons that are moving around the nucleus. The electrons are an example of elementary particles. The nucleus is done by protons and the neutrons. The protons and neutrons are not elementary particles because they are too big. They are made by the quarks up and down. These are elementary particles. So 3 of these 30 elementary particles belongs to everything that has to do with everything that is around us. Many of these elementary particles have been discovered studying the cosmic rays. You know what is a cosmic ray? It's an object coming from space. Why is it so important to study this object? Why you are here? The answer is that we pretend to better understand our universe, the world that is around us, studying this small object.